Alright, boys and girls, welcome back to the drive-thru for a remix special live recording, 6th bell. How's everybody doing today? Thank you, Hannah. Susan, how are you? Very good, very good. Okay, so we are continuing our little walk through probability. Today we're doing the probability of multiple events. So, a lot of times multiple events have ands or ors. Those are really different words. Think about it. If your mom and dad told you, you've got to clean the room or take a nap, you'd be like, sweet. Okay? If they said, you've got to clean your room and take a nap, well, now you don't have a choice. You have to clean the room. So the and or are powerful words when it comes to decision making, and that's what we're going to be studying today. So what are dependent events? They're exactly what they sound like. An event that depends on another event happening, or the likelihood changes if something else happens. So let me ask you this. If I just said, what's the probability that if I randomly select a student at Sycamore High School, that student plays football? The answer would be like 10%. But if I said, if I selected a boy, what is the probability that that person plays football? Now the probability goes up to like 22%. Because almost all of the players on the football team are boys. So those would be dependent. Okay? Being a boy changes the likelihood that you play football here. Does that make sense? Where independent events have absolutely no effect on each other. So, let's say, what is the probability that I toss a head and roll an even number with a die? Well, my coin toss had absolutely no effect on my roll. So those would be independent events. Okay? And there's a test. So if we run that scenario, in fact, let's run a little easier scenario. Let's say we're going to toss a coin 3 times. So we've got toss number 1, toss number 2, and toss number 3. What's the probability that I toss heads all 3 times? Well, it probably can't be 3. It's got to be between 0 and 1, right? Our answers are always less than 1 and bigger than 0. Well, let's look at it. Let's write all the ways we could toss 3 coins. Okay, so the first one, I could get a tail on the first one, tail on the second one, tail on the third one. I could get a tail on the first one, a tail on the second one, and a head on the third one. I get a tail on the first one, a head on the second one, and a tail on the third one. I could get a tail on the first one, a head on the second one, and a head on the third one. I think that's all the ways that I could toss a tail first, right? My next one I'll do will be head, 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 3 heads, and then head, head, tail. You can see I'm kind of mimicking this one. Head, tail, head, head, tail, tail. Can anyone come up with another opportunity or option for tossing a coin 3 times? There are indeed 8 different scenarios. Okay? How many of them have all of them as heads? So the probability is actually, the probability of tossing a head 3 times in a row is 1 out of 8. Well, let's test to see if these things are independent. What was the probability of tossing a head on the first one? 1/2, right? Your probability of tossing a head is 1/2. It's 50-50. And what's the probability of tossing a head on the second one? And on the third one? And what's 1/2 times 1/2 times 1/2? We just multiplied fractions last chapter. What is that? It's 1/8. And so that is the math that you use to prove that these are independent events. Meaning, you're not more likely to toss a tail on the second one or a head on the second one than on the first one. Okay. All right, so let's take a look at these and do some practice. There's a picnic, there's a cooler of sodas, and there's a basket of chips. You've got 10 sodas that are regular and 5 that are diet. You've got 10 chips that are regular and 5 that are fat-free. If you just randomly grab a drink and grab a bag of chips, what is the probability that you get a regular drink and fat-free chips? Well, is there anything about the drink that you grab that will change the likelihood of the types of chips that you'll grab? No, because we said you're just blindly picking them. Now here's where statistics gets weird. In the real world, people don't pick blind in these scenarios, do they? They don't. And would you say that in the real world, if someone picked a diet drink, do you think that they would be more likely to pick the fat-free chips? They would be. I think you could absolutely make that claim, and you could prove it using statistics. So that's the hard part of this section, is there's a lot of context, meaning you have to actually understand what they're saying and what you're doing. But I also want to remind you that last year, no one in academic Algebra 2 did any of this. So even if you learn this a little bit and you fail at some of it, you're ahead of everyone that I taught last year. And I can promise you, if college is something that you're thinking about doing, you're absolutely going to take a probability and statistics class. It's a mandatory class in almost every college for every major. Okay? And I will tell you this, you probably won't have to take algebra or calculus, but you will have to take probability and statistics because everyone needs to understand how these numbers are working because there's just so much data everywhere. So, in this question, it's pretty easy. What's the probability that you pick a regular drink? Well, there's 10 out of them out of 15. And since these are independent events, you're just going to multiply that by the probability that you pick a reduced fat or a fat-free chips, which is 5 out of 15. And we learned last week that to multiply fractions, you just multiply across the top, multiply across the bottom. But let's reduce these because it's easier. Do you understand that this is 2/3? Divide them both by 5. And this is 1/3. So the answer is going to be 2/9, or about 22.2%. Okay? So if that's what you want, if you definitely want a regular drink and fat-free chips, you're not very likely to get what you want in that scenario. Okay? If you pick randomly. All right, now let's look at the difference between that one and the second one. The second one, you have some dependent stuff going on here. I know that you guys don't know anything about cards, so I'll just tell you some basics. There are 52 cards in a deck. 26 of them are black, and 26 of them are red. Now, of these red, 13 are diamonds, 13 are hearts. Of these black, 13 are clubs, 13 are spades. Okay? But if you draw two cards out of a deck, what is the probability that both of the cards are red? Well, this is some funny math. You might think that it's like maybe it's 2 out of 26 or 2 out of 52 or something like that, but you have to actually consider these to be two separate events. So what's the probability that you pick a red card on your first draw? It would be 1/2. Excellent. Now I will write that as 26 out of 52. There are 26 red cards, and there are 52 cards total. Now, on the second one, your odds actually change a little bit because you just picked a red card. One of them's gone. So how many red cards remain? 25. Okay, and how many cards remain? 51. So if I reduce this to 1/2, the answer is 25 out of, let's see, 102. So that's just like 24.6% or something like that. Okay? So that's how you do that one. All right, so now we've talked about dependent and independent. Now we're going to talk about mutually exclusive groups. Lots of vocabulary in this stuff. To be mutually exclusive means that there are two things that cannot happen at the same time, or there are two sets of things that cannot share a member. So the example that I used here is if you roll a die, the number is either going to be odd or it's going to be even. It cannot be odd and even at the same time, because those are mutually exclusive. Just so you know, most events are not mutually exclusive. A lot of times you can be a member of two groups. And this example we're going to use is just going to take a straw poll of you guys real quick. I might even have to lie about some of the results. But just raise your hand if you're on this list of people. I just grabbed some people from class, okay? If you're really into music, super into music. Okay, so we got Alyssa and Luca and Kennedy and okay. Anybody else really into music on that list? Carter didn't make the list. He was in the bathroom. Sorry, Carter. No big deal. Okay? Yeah, you were taking your test. I didn't want to bother you. All right. What about the people on this list that are super into sports? So Luca and Hannah T. and Hannah Phillips. Okay? And Kennedy and Sujin and Alyssa. Okay? Phoebe, sorry, didn't make the cut. All right, so now look, hear me out on this. What is the probability, okay, that people are into music? How many people are on the list? Oh, whoops, I meant to put 10, but anyway. The probability that they are into music is 4 ninths. What is the probability that they're into sports? 6 ninths. So, what is the probability that someone is into music or into sports? Well, normally when we say or, we add, right? So it would be 4 ninths, bless you, plus 6 ninths. And what do you get for that answer? 10/18. No. 10/9. Oh, hold on. You're saying that the probability, what is the probability that someone likes music or sports? Well, we're saying that's more than 100%. It doesn't make any sense. Like, that literally doesn't make any mathematical sense. You can't be more than 100% of anything. Because what happened was, we counted Luca twice. We counted Kennedy twice. We counted Hannah T twice. And we counted Alyssa twice. There are 4 people on this list that are into music and sports. Okay? So what we have to do is subtract them. And the answer is actually 6 ninths. Okay? So, what does that mean? Well, that's because Sarah and Alex and Amber, they're not into either, which is totally fine, right? So if we're looking for the people in that group that are into music or sports, we could also just look for the people in that group that are into neither. Those two things are mutually exclusive. Okay? So that's mutually exclusive events. And the most important things that you can know about this is if 2 events are not mutually exclusive, the probability of A or B happening is equal to the probability of A happening plus the probability of B happening minus the probability of A and B happening. Okay? So you take the people that like music, you add them to the people that like sports, and then you subtract the people that like both so you don't count them twice. Okay, so now we're going to move on and do your 11.3 worksheet. We're going to do some of these together. I hate the first 4 questions. I think they would actually make you more frustrated than anything else, and I think you guys might even debate whether or not they are dependent or independent. That debate would be healthy, but we just don't have time for it on the video, so we're skipping it. It says Q and R are independent events. If they are independent, then the probability of A and B happening is the probability of A times the probability of B. That's what we learned in our first one. So, in number 5, we've just got to do 1/8 times 2/5, which is 2/40, or 1/20, or 0.05, or 5%. Okay? In number 6, they're looking for the probability of Q and R. Well, that's the probability of Q times the probability of R. So that's 0.8 times 0.2, which is 0.16. I want you to notice that "and" in probability usually makes things less likely to happen. Right? What's the probability that it rains today? I don't know, 60%. What's the probability that it rains today and you go fishing? Well, that's way lower than 60%, you know? It has to rain and you have to go fishing, and those things are not both likely to happen. So "and" in this case reduces the probability. Let's do number 9. Suppose you have 7 CDs in a box. 4 of them are rock, 1 of them is jazz, and 2 of them are country. I don't even know if you guys know what CDs are, but they're round silver discs that play music or other audio files or video files. Okay. All right, so you're going to put the CD back in the box. So these are independent events, meaning your likelihood of watching country tomorrow doesn't change because listening to country tomorrow doesn't change because you listen to country today. So this one is just going to be 2/7 for day 1, 2/7 for day 2. So you get 4/49, or just over 4%. So you're not, just over 8%. So you are not very likely to listen to country on back-to-back days. And you should all be thankful for that. All right, sorry. So now we're looking for probability of M or N, but they are mutually exclusive. So if they're mutually exclusive, the probability of M or N is simply the probability of M plus the probability of N. Okay? So, for number 13, I'll just do 3/4 plus 1/6. Adding fractions. What do we need? Liz? Common denominator. So we'll multiply that by 2/2. You get 9/12 plus 2/12, and the answer is 11/12. Okay? For number 14, well, percents are much easier. You just do 10% plus 45%, and the answer is 55%. No, or 0.55. Yep. Those are both fine. Or 55/100ths. All right, moving on. A fair number cube is tossed. What is the probability that you get an even or a 3? Well, what we have to do is decide if these are mutually exclusive. Can a number be even and also be 3? It cannot. So this is just the probability of it being even plus the probability of it being 3. What's the probability of the number being even on a die? 1/2, 3/6, right? What's the probability of it being a 3? 1/6. Only one of those numbers is a 3. So you add those up, you get 3/6 plus 1/6. The answer is 4/6, or 2/3, or 67%. Can a number be less than 2 and also be even? It cannot. Not if it's a number on a die. So, what's the probability that it's less than 2? That's 1/6, right? There's only one number less than 2. What's the probability that it's even? 1/2. Very good. So this is the same answer. You get 2/3. Okay? How about number 20, Luca? Luca's cotton on. These are all the same answer. Can you be a prime number and also be a 4? You cannot. 4 is not a prime number. Now, what are the prime numbers on a die? 1. Oh, you know what? Is 2 a prime number? I seriously don't know. I think it is. Is it the only even prime? Because the number's prime if it's only divisible by 1 and itself. 2 is only divisible by 1 and itself. Must be the only even prime. But you can Google that for me if you care. Honestly, I don't know the answer to that question. I probably should because I'm a math teacher, but I'm not really super into that kind of stuff. All right, so what's the probability of it being prime? 4/6. What's the probability of it being a 4? 1/6. So this one, the answer is 5/6. Okay? Almost done. All right. Now you've got a drawer with 5 pairs of white socks, 3 pairs of black socks, and 1 pair of red socks. You choose 1 pair of socks at random each morning with your eyes closed, but you do not put those stanky things back. So, for number 26, these would be conditional probabilities, okay? So, what's the probability that you select a black sock on Monday? 3 out of how many pairs do we have? 9. Now, given that you selected black socks on Monday, what's the probability that you select a white sock on Tuesday? There's 5 white socks, but how many pairs of socks are left? 8. There's only 8 pairs left. That's where the probability changes because it's dependent. Okay? And that is 15 out of 72. I'm not sure what that is as a decimal. 15 divided by 72. It's about 20. Whoa. It is about 20.8%. Okay? Because we didn't select a... Good question. The question is, why wasn't this one 4 out of 8? Because we didn't select a white pair of socks on Monday. We selected a black pair of socks. Okay? Good question. All right, the final one, 27. What's the probability you select red socks on Monday and black socks on Tuesday? Well, the probability that you select a red sock on Monday is 1/9. Get out of here. Oh, well. And the probability that you select black socks on Tuesday would be 3/8. So it's 3 out of 72, so this is not likely to happen at all. No. Okay? And that does the video. Have a great day. Boom!